All right, so that's sorted arrays. How does that compare to a binary search tree? Well, a binary search tree, everything is going to be considered a node in the tree, and each node is going to have a pointer to its left subtree, a pointer to its right subtree, a pointer to a parent node. That's not strictly necessary, but you can have a pointer that goes back to your parent, which makes it easier to traverse up and down the tree, and a piece of data, or some sort of key value. So that, for example, would be the 8. So it's not just a piece of data. We're going to call it a key most of the time because we have to be able to compare keys to one another. So compare the 3 to the 8, for example, and know that the 8 is greater than the 3. A binary search tree has these properties. All keys found in the left subtree must be less than the key of the current node. So, for example, if I take the current node as the 6, everything to the left of it, so following its left child pointer, has to be less than 6. And then likewise, everything that's found in the right subtree must be greater than or equal to. You can put the equal to on sort of either side. For the purposes of these slides, we're not going to have any duplicates, so it's not going to be something we have to deal with in the slides. All right, so given a set of keys, is a binary search tree unique? So we're going to ignore ties for this, and by unique, I mean can you arrange the nodes, can you move nodes around in any sort of way and still have a valid binary search tree? The answer to that is no, and we'll have some examples in the upcoming slides. All right, but before we talk more about binary search trees, I want to compare graphs and trees since we just got done speaking a lot about graphs. So a tree is really just a special type of graph. Trees cannot contain cycles, so it's an acyclic graph. They always have directed edges. They have a single source node, so that's a node with no incoming edges. That's sort of if you ignore the edges that go back to the parent, so the parent pointers. So that's, you would ignore that there and here. And typically we think of a tree as just having the arrows going down. All trees have exactly one parent. Sorry, all vertices in a tree have exactly one parent. So you'll have an n degree of 1 for every node, except for the root, which has no parent. And again, we're ignoring any pointers back to parents. Trees always have n-1 edges. Again, ignoring arrows back to parents. So how does this compare to a heap? Well, a heap is always balanced. Binary search trees are not necessarily balanced. So a heap, you always add nodes by putting it in the next available slot and then bubbling up or down. For a binary search tree, you could, for example, put everything sort of anywhere in the tree that you want, and it doesn't have to be balanced. Balanced meaning you have the same number of nodes going to the left as you do to the right, or off by 1 at most, or off by a smaller number at most. And they have different properties. So where are the lesser values? Well, in a binary search tree, we know that values that are less than the current node are to the left, and we know for a heap they are up the tree. So the minimum in a heap is at the root, and that's not where it is for a binary search tree, and we'll talk more about that in a few slides.